Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 82. Now in the previous lecture, we were discussing about the atmospheres of various planets, and I was telling you about the interesting mass problem with Pluto and also how its atmosphere unexpectedly kept growing thicker, and suddenly it was found to be growing thinner. On that note, I'll tell you one more aspect about Pluto in this lecture. It is that alongside its mass and atmosphere being problematic, now there is yet another aspect about Pluto, yet another major reason, yet another major reason why Pluto was demoted as a dwarf planet, is that, see, I told you, right? The reason why Pluto was demoted as a dwarf planet was because, it is lying very close to the Kuiper belt, and beyond the Kuiper belt is the Oort belt. I think in lecture 80, I was imprecise when I said the Kuiper belt and Oort belt are both close to Pluto. No, there's Pluto, then there's the Kuiper belt, and then there's the Oort belt. Okay, please note this correction. All right. So, and due to the presence of this Kuiper belt and lots of comets, the mass and atmosphere of Pluto is problematic, and it keeps changing, is what I said. On top of that, that was also one reason, but the predominant reason why Pluto has been demoted to a dwarf planet is because of this point. I want to use this technical phrase, though the phrase used by astronomers is that Pluto has not cleared the neighborhood. Now what is meant by clearing the neighborhood? Well, what it refers to is that, I did mention in lecture 80 that the orbit of Pluto, is susceptible to a lot of change. Why is that due to? It is because in the orbit of Pluto, very in the vicinity of the orbit. When I say orbit, I'm talking about Pluto's orbit around the Sun. In the vicinity of the orbit of Pluto lie, at least some, if not a lot. So in the vicinity of the orbit of Pluto lie at least some, if not a lot of, similar, I would say, I'll phrase it better. So in the vicinity of the orbit of Pluto lie at least some, if not a lot of celestial objects, I'll put it this way. With comparable mass. Now, as a result, what happens is that, it is of course perhaps on course to collision, but not just that. So if you consider a planet such as Earth, its orbit around the Sun is clearly neat, okay, and is devoid of traffic. What I mean by devoid of traffic here is that Earth's gravity is sufficiently strong enough that any other object which has a higher gravitational pull than Earth, for example, let's say Jupiter or Saturn, they're all away, significantly away from the orbit of Earth. But with Pluto, right, if there are certain celestial objects or entities, in fact, entities sound better. Okay, so when there are celestial objects or entities which are in the vicinity of Pluto, well, there is also going to be the attraction between Pluto and this planet to be considered, right? And that planet will be interfering with the orbit of Pluto around the Sun. One such, I'm saying planet, for example, if I say Neptune, it's a planet, but that celestial entity is going to interfere with the orbit of Pluto. That's a very important point. For example, I think approximately in 2003 or 2004, there was this dwarf planet, not Pluto, but another dwarf planet called Eris or Eris, a dwarf planet similar in size to Pluto. Was convincingly detected, okay, was convincingly detected in the Kuiper belt. Now, what does this imply? Well, this implies that clearly Pluto has not cleared the neighborhood. So therefore, on top of being constantly in touch with comets, etc., even gravitationally, there's problem due to entities such as Eris. Okay. In fact, there was a controversy about Eris also. 20 years ago, it was kind of understood that Eris was heavier than Pluto. But currently, they say that no, there are some issues. So Pluto is perhaps heavier. But nonetheless, that's why I said that it is similar in size to Pluto. I was careful enough here. Okay. So this is not the end of the story. I mean, the relative sizes between Eris and Pluto. But nonetheless, what is clear enough is that Pluto is not the only, is not the only heavy object which has sole access to its orbit. Okay, right? So therefore, the point is, it has not cleared the neighborhood of sufficiently enough entities. All right, so that is also why this implies overall, okay, right? The existence of Eris and several other comets in the vicinity of Pluto overall imply that Pluto demoted to a dwarf planet. Now, I thought that in lecture 80, I had actually forgotten to mention this point about clearing of neighborhood and then Pluto being a dwarf planet. So I want to emphasize on that fact right over here, because see, alongside the idea that the mass of Pluto is problematic due to the atmosphere constantly changing, the more important reason for why Pluto was demoted is Pluto having not cleared the neighborhood, okay, of similarly sized celestial entities. For example, Eris, the dwarf planet, etc. So this is one very important point about Pluto. So I think with this, we have completed our discourse about Pluto and why it's a dwarf planet, etc. I'll now move on to the Earth's atmosphere, especially in the context of early Earth atmosphere, and how that leads to this fascinating idea of prebiotic chemistry. So if you think about it, I think in lecture 80, I had ended by giving you the surface temperature of Earth. Okay, so the surface temperature, I'm just going to call this T sub S, on Earth is around 285 Kelvin. We were comparing, the surface temperature of Earth with the surface temperature of other planets, such as, for example, Venus, Mars were also mentioned. That of Mars is around, if I'm correct, 220 Kelvin. Correct me if I'm wrong. So this is 220 Kelvin. Okay. Now, this was the closest number, So, of course, Mars is also pretty close to Earth, right? Mars is the next planet. It is our neighbor for all practical purposes. Okay. So, when it comes to the question of, life on Mars, well, this does indicate that maybe, if there is a way to perhaps heat up Mars sufficiently, maybe we could live. However, that is fraught with a lot of challenges. The most challenging aspect with Mars is that now, despite the somewhat close surface temperature, I'm just indicating with T sub S, the surface pressure presents a problem. Okay, so the surface pressure on Earth is what? Roughly 1 atmosphere, right? Now on Mars, okay, right? On Mars is less than 1% of this actually. Okay, the average atmospheric pressure, right? The surface pressure on Mars is less than 1% of Earth. You can calculate it, okay? You can get the values in terms of pascals, bars, etc., etc. So this is approximately less than 1% even. Now, as a consequence, the problem is that Mars's atmosphere is not as pronounced as Earth, okay? So despite the somewhat close temperature of Mars, the atmosphere of Mars is a lot less dense. When you compare, density in terms of mass per unit volume, right? Mars, I think, is less than 2%, not less than, is only about 2% as dense as Earth, the atmosphere. When you consider the atmosphere of Mars is only about 2% as dense as the atmosphere of Earth. Now, this is also a problem, correct? Okay. Now, because of the significantly more diffuse nature of Mars's atmosphere and its significant less density, what happens is that in Mars, it is actually not easy. This is an understatement, okay, right? To maintain a constant or close enough to being constant, okay, a constant temperature range for the surface temperature. Are we clear? Okay, because the atmosphere is so thin. Now, this is why I'm sure that, like we discussed in the last class, you would be appreciating the atmosphere of Earth much more because of this value, because it is sufficiently enough number density. The surface temperature of Earth is kept a constant. It goes back to the greenhouse effect, etc., right? This luxury Earth has that Mars does not have. And that is why this overall implies life on Mars is a great challenge as of today, okay? But of course, there were planets, there were proposals, including one by Elon Musk of SpaceX and several space agencies to try to, nuke Mars and heat up the temperatures and see if you could build some atmosphere there, etc., etc. It would be very, very fascinating to watch all of them play out, if at all they do, in the, I don't know, hopefully somewhat near or far future, way beyond our generation also. So some exciting possibilities are there, but scientifically, it's a huge challenge to overcome. Please note this point. Okay, all right. So this was the topic on the comparison between Earth and Mars's atmosphere. Now we shall go and talk about this super cool idea of prebiotic chemistry. So the next topic for our discussion is what is called as prebiotic chemistry. Now, very roughly translated, prebiotic chemistry refers to how might the molecules, especially the biomolecules relevant to life, might have formed on Earth. So having discussed so much about the significance of Earth's atmosphere, right? Somehow, starting off with some primitive atmosphere, we are here today, basking in our glory of various life forms surrounding us, various living and non-living forms surrounding us, right? So how might life have originated, very roughly speaking, and how might the molecules responsible for life may have been formed? So this is the fascinating question that this field of prebiotic chemistry seeks to explore and answer. Okay. Now, what is one suitable beginning point to discuss, this topic of prebiotic chemistry? A suitable starting point. Now, this first question, right? What might be a suitable starting point was asked once by Miller and Urey, okay, by two faculty, I think in the University of Chicago, if I'm correct, okay, right? So this question was first asked by Miller and Urey. I'm not sure if both of them were faculty. I think one of them was a postdoc of the other. I'll have to look up and I'll get back to you. Okay, I forgot the details. So these people were overall asking this question of what is the suitable starting point. Now, I think it was Urey who postulated that the solar system, early stages, because I think I told you earlier, right? Almost all the planets were in their primitive form, were formed almost simultaneously along with the generation of the solar system. Okay. Now, at the early stages, because all the planets were, simultaneously formed, the atmosphere of Earth should perhaps be a gassy mixture similar to, say, something like Jupiter. Now, what is the logic behind Jupiter? Why not, say Uranus or Neptune? Well, the Jupiter is closer than, Saturn or Uranus. Okay, that's one point. The other idea is that the outer planets such as Jupiter, etc., have evolved less over time vis-a-vis, like the inner planets, the rocky planets. That is because they are further away from the sun. Well, of course, there could be a lot of impact by asteroids and meteorites, etc., etc. But when it comes to the gas composition, because the chemical diversity in a planet such as Jupiter is way less than what you would note on some planets such as Earth. Okay, so perhaps that because Jupiter has more or less, A, it's more or less close to the Earth, and B, not more or less, it is close to the Earth than the other gassy planets. Okay, that's one point. And the other idea that change of composition of Jupiter is way less than say some of the other planets which are closer to Sun. Okay, so these two made Urey hypothesize that perhaps that in the early stages, right, Earth may be containing gases similar to what are present on Jupiter's surface. So he postulated that, well, why don't we start off with a mixture containing hydrogen, ammonia, and CH4 gas. So these were postulated to be present, as part of early Earth atmosphere, all these gases. So the question now was, okay, we now have a starting point. Now, from this starting point, under putative early Earth conditions, could we generate the larger molecules? That is the next question. In other words, the question is, under putative early Earth conditions, could a mixture of hydrogen, ammonia, and methane, all in the gaseous state, all of them gases, okay, right, lead to more complicated molecules, right, which could eventually be connected with the molecules of life itself. we're talking about the RNAs, DNAs, etc., starting from very humble beginnings. We're talking about, molecules containing 2 atoms, 4 atoms, and 5 atoms, something like that. Is it possible even? Okay. Now, to answer this question, you must first define what the putative early Earth conditions could be, right? To do that, what they presumed was, so what Miller and Urey presumed was that the early Earth, would be subject to a lot more cosmic wave bombardment because the protective layer of atmosphere was not there. Okay, subject to a lot more, I would call it high energy radiations. So therefore, to mimic the early Earth conditions, perhaps subjecting these molecules to electric discharge, which implies a model could be to subject these molecules, H2, ammonia, and CH4, to electric discharge and check what products emerge. Now, I've made 3 exclamatory marks because this was a very profound thought, right? So you assume that, okay, perhaps some intense electric discharge, right, could be some kind of a mimic to the early Earth conditions, the proposed putative early Earth conditions, which were constantly bombarded by, let's say, cosmic rays, high energy radiations, gamma rays, X-rays, maybe, who knows, right? Yeah, all these radiations, etc. So this was their premise. So with this premise, they subjected these molecules to electric discharge. In fact, this is the exact experimental setup. You may even look up in class 12 biology textbook. I don't know if chemistry textbook has it, but I'm sure biology has it, because this is also the beginning of astrobiology. So the fact that your molecules as small as this can eventually lead to life forms, right, is what the area of astrobiology is concerned with. Okay, so prebiotic chemistry is just one step away from the area of astrobiology. All right, so just note this. Okay, so now let us look at what the products were formed actually by subjecting this to electric discharge. What all products were formed? Okay, so I will first give you the answer as to what all products were formed. In fact, what products were formed depends on how much time you give the reaction mixture, right? Milley and Urey performed these experiments in the early 1950s, if I'm correct, okay, or maybe late 1940s. Immediately, they were looking for the various products. And more recently, we're talking about I think the late 2000s, okay, the late 2000s or perhaps early 2010s or 2010, 11, somewhere around that time. They also reanalyzed the mixtures, okay, and they found that, I'll give you the answer first. So the products formed included a remarkable array of organic molecules, in particular amino acids, some nucleic acid bases, carbohydrates, etc. In other words, a lot of molecules which typify, okay, right, which typify the biomolecules which are eventually going to assemble to give rise to life, okay, which implies that a lot of molecules of biological interest could indeed be formed. So what I've written here is a lot of molecules of biological interest could indeed be formed. Now, this was a stunning revelation. And of course, this question, this model of early Earth, right? A model for early Earth is highly debated. I mean, why should it only be H2, ammonia, and CH4 gas? These gases were called as reducing gases. Now, a lot of geologists have also modeled early volcanic scenarios, wherein, you have a mixture of carbon dioxide, carbon monoxide, what else? Let me just take a look. So you have a mixture of carbon dioxide, carbon monoxide, and nitrogen. Okay, right? So they were also postulated, but by and large, this was the first exhibition of the idea that a lot of molecules of biological interest could be generated from very simple molecules if you subject them to electric discharge. Okay, now we shall now look into the mechanism of formation of some of these molecules. Okay, what all organic molecules are formed and how might they be formed. That is what we shall be looking now. Okay, so broad mechanism of how these organic molecules are formed. I'll rather put them as bioorganic molecules. Okay, so how are what are the molecules formed and how are they formed? So the first thing is, starting from H2O, right? I think you have H2, ammonia, and methane, right? So, a lot of these molecules are there, okay? And so the first thing we shall be looking into is how do you get HCN, okay, right? For example, you start with ammonia, right? And let's say that ammonia is subject to, electric discharge, which is equivalent to photodissociation, and you generate NH2 radical and hydrogen radical. Now, subsequent to this, what happens is that the NH2 radical reacts with your methane. This is going to result in the formation of a CH3 radical, all in the gas phase, okay, plus regeneration of ammonia. Now, see, the beauty with your Urey-Miller process is that it also kind of alludes to a catalytic happening, right? You start off with ammonia and you generate ammonia, and so therefore this could be sustained, okay, right? So the one remarkable tenet from the Urey-Miller experiment is that it was also able to explain possible catalysis, which is very helpful for the origin of life itself. Okay, so this is the second step, and subsequently your NH2, the radical formed in this step, is going to react with your CH3 radical to be giving CH3NH2. If I'm correct, its name is methylamine. So once this is formed, your methylamine, so you've already formed a CN bond, right? Now this is subject to intense oxidation. Okay, so it is subject to intense oxidation, and this is going to be resulting in HCN, and if I'm correct, 2H2. So what have we generated? We've already generated HCN, okay, from the simple mixture of H2, NH3, and CH4. Okay, we'll stop here at this stage, and I'll tell you in the next lecture as to how HCN and some other molecules, for example, including water. Hey, water is not part of this mixture, right? So how might have water formed, and what may have happened en route to the formation of a lot of biomolecules. So in this lecture, I started with discussing the major reason why Pluto is no longer called a planet, and followed by that I was discussing about the the Earth's atmosphere and the Mars's atmosphere. I was comparing and why it is challenging to propose life on Mars. And followed by that, we started the topic of discussion on prebiotic chemistry. And I had given you the big picture behind the Urey-Miller synthesis. And we are looking at the details of how specific molecules are getting formed via the Urey-Miller mechanism. On that note, I'll meet you all in lecture number 83. Thanks a lot.